Okay, so final talk of this session. This is Gavin Ball at UQAM, talking about closed G2 structures with conformally flat metrics.
Thanks, Mark, and thanks to the organisers for inviting me to talk. So the title of my talk is Closed G2 Structures with Conformally Flat Metric, but I'm going to start the talk by talking about some more sort of general problems that I certainly haven't solved, but I've only thought a bit about that I think might be interesting for people. So one of the things I like about giving a talk at a workshop like this is that you can start your talk with a sentence like this. So let's take a G2 structure on some 7-manifold M, and we know that it defines a Riemannian metric on M and a volume form that is the volume form of that Riemannian metric via the following formula. So if I want to see what, well, you just have the formula here. And it looks a bit funny because it looks like you're getting two pieces of information from one equation, but the key is that the volume form should be associated to the metric N, should be associated to the metric G, so we have some extra kind of scaling behavior that's fixed by that condition. Okay, so what we get is a map then from G2 structures to Riemannian metrics on our manifold. And if I want my G2 structure to satisfy some special extra condition, for example, if I want it to be torsion free, then those special conditions are reflected in the geometry of the metric on M. So the most famous example of this definitely is that if phi is torsion free, then the metric actually turns out to have holonomy group contained in G2, from which it follows that the metric is Ricci flat. So kind of some special first order condition for the 3 form implies some special condition for the metric. Okay, but in the study of manifolds with special holonomy, you often want to consider G2 structures that aren't torsion free. They satisfy some weaker conditions that are usually first order. And when we consider these kind of conditions, there's usually two natural cases that are interesting. So they're the closed G2 structures. Those are the G2 structures for which the 3 form is closed. And there are the co-closed G2 structures, those for which the 4 form that you get by taking the Hodge star of the 3 form with respect to the metric and volume form induced by the 3 form. You just want that 4 form to be closed as well. So we call those co-closed G2 structures. And these two families of conditions are sort of, they intersect at the torsion-free condition, but otherwise they have somewhat different flavors, I would say. But the kind of techniques that I'm going to talk about are potentially applicable to both. So the kind of question that I'm interested in the first part of the talk, and then the second part of the talk is going to be a special case, is suppose that our 3 form satisfies one of these weaker conditions. Is there anything interesting that you can say about the metric induced by the 3 form? So I said when it satisfies both of these conditions, there's something very interesting you can say, but maybe if you just want to relax it, is there something we can say? And maybe more specifically, there's this prescribed metric problem. So if you come to me with a Riemannian metric on M, can I find a G2 structure that satisfies one of these weaker conditions that actually induces this metric that you've just given me? And this second question is only really interesting if I'm asking for the 3 form to satisfy one of these weaker conditions, because locally, every Riemannian metric is induced by some G2 structure. The argument for that goes like this. So if I have my metric and I consider a locally defined orthonormal coframe for that metric, then the following G2 structure, sort of the standard G2 structure written in terms of this coframe, is just going to induce that metric. But there's no guarantee that this G2 structure is going to be closed or co-closed. Okay. Now, this second problem, this prescribed metric problem, for the generic metric, it's not going to have a solution. So there will not exist, even kind of locally, a closed or co-closed G2 structure that induces this metric. And you can see that because there's some simple sort of counting argument. So a Riemannian metric on a 7-manifold, if you think of it, it's a section of the bundle of symmetric 2 tensors. And then you take away the action of the diffeomorphism group. That's 21 functions of 7 variables. On the other hand, a closed G2 structure, you could say locally, well, it's definitely exact. And you can kind of push that argument to say that a closed G2 structure, again, modulo the action of the diffeomorphism group, depends on 8 functions of 7 variables. So that 8 is less than 21. So there's no way that if you take your G2 structures and vary them in your kind of family that depends on 8 functions of 7 variables, you just can't fill out the space of Riemannian metrics, which is going to depend on 21 functions of 7 variables. So there's no chance that your metric, if you pick a generic one, is going to be induced by a closed G2 structure. And a similar argument works for co-closed G2 structures. You can show that they depend modulo diffeomorphism on 13 functions of 7 variables. So again, you can't expect to get the generic Riemannian metric. Okay, so this prescribed metric problem is sort of an overdetermined system. I realize here I've written system of PDE, but that's not strictly true. It's just an algebraic system. But you want to analyze it using the theory of the overdetermined systems of PDE. Generically, it won't have solutions, and you can sort of run this exterior differential systems analysis, and you get relatively complicated integrability conditions that arise essentially from the what you might call the Bianchi identities of the metric. And we'll see an example of that later on when I focus on closed G2 structures, but I just want to say that these problems, from the point of view of exterior differential systems, turn out to be quite hard. You could think of them as analogs maybe of isometric embedding problems in the overdetermined region where the codimension is relatively small, or of kind of prescribed Ricci curvature, the prescribed Ricci curvature problem for a metric. Okay. So now I want to focus just on closed G2 structures. This is maybe more interesting from the point of view of construction of compact manifolds with special holonomy. But like I say, the kind of techniques that I'm going to describe could be used in the co-closed case as well. So for the rest of the talk, I'm considering only closed G2 structures. And the metrics induced by these are already special because Robert Bryant has shown that the scalar curvature of this induced metric is always non-positive. So if tau denotes the torsion 2 form of phi, so this is the 2 form that's defined by the equation d star phi equals tau wedge phi, then Robert showed that the scalar curvature of G is actually a half of the norm squared of tau, which is kind of interesting because the left-hand side looks like it should depend on maybe 2 derivatives, but the right-hand side, the torsion, we got it by just differentiating the structure once. So the right-hand side is actually a first order object. And more generally, certain components of the Riemannian curvature tensor of G phi are determined by tau, as I'm going to explain. To explain that, I need to do a little bit of representation theory. So if K is the space of algebraic curvature tensors on R7, say, then there's an SO7 irreducible decomposition of K. It's kind of well known in Riemannian geometry. It decomposes into a trivial piece, symmetric traceless 2 tensor, and then kind of a space that corresponds to the valid curvature. So this corresponds to the scalar curvature, the traceless Ricci curvature, and the valid curvature. Now I'm thinking about G2 structures. So the appropriate group to decompose my space under is not SO7, but it's subgroup G2 of SO7. And these first 2 spaces remain irreducible under this G2 action, but the space of algebraic valid tensors actually has an irreducible decomposition into another copy of the symmetric traceless 2 tensors on R7. And these 2 G2 representation spaces of dimension 64 and 77. So under the action of G2, the space of algebraic curvature tensors has a fully decomposed thing has 5 components. So we get 5 kind of basic tensors that could be formed from the Riemannian curvature on a manifold that has G2 structure. So it's the scalar curvature, the traceless Ricci curvature, and then these different pieces of the valid curvature. And now the Ricci curvature and this W27, they both live in the space of symmetric traceless 2 form, so you could add, you could take linear combinations of those as well. Now for a closed G2 structure, it turns out that the first Bianchi identity implies the following relations. So you get Robert's formula for the scalar curvature. You get a formula that I'm not going to write down, also due to Robert, that describes the traceless Ricci curvature in terms of tau and d tau. So this 3 form d tau. You get a formula for the 27-dimensional piece of the valid curvature in terms of tau and d tau again. That looks very similar to the formula for the traceless Ricci curvature. And you get a formula for the 64-dimensional piece of the valid curvature in terms of the covariant derivative of tau with respect to some connection. And so in fact, the only thing that isn't determined essentially by tau or its derivatives is this W77. And this W77 is exactly what the curvature of a torsion-free G2 structure looks like. So everything else can be described in terms of tau and kind of derivatives of tau. Okay, so in fact, you can use Cartan's method of equivalence to show that d tau, this W64 and this W77 kind of form a complete set of second order diffeomorphism invariants for a closed G2 structure phi. So what that means, if you have some kind of invariant expression, some expression that's invariant under the diffeomorphism group of this closed G2 structure that is polynomial in derivatives up to second order, then it's going to be expressed in terms of tau, d tau, W64 and W77. Okay, and that's going to be important later in the talk. This kind of fact is going to be crucial later on. Okay, so this is kind of the basic local differential geometry, the kind of curvature of closed G2 structures. I wanted to say a little bit about global issues. So one of the kind of I think, important things that we don't know is that we don't know much about the topology of compact manifolds that admit closed G2 structures. So in fact, it's currently unknown whether, if you know that you have a simply connected compact and spin 7 manifold that admits a closed G2 structure, we don't know if that actually says anything more about the topology. So in particular, we don't even know if the 7 sphere admits a closed G2 structure. And this kind of thing, this kind of problem is maybe relevant to the Laplacian flow, because the Laplacian flow is supposed to start on a closed G2 structure and flow towards a torsion-free G2 structure. But if we don't know much about kind of what our initial conditions could be, that's going to be maybe a problem in using the flow. So I just wanted to say, in light of this lack of knowledge, it might be worth investigating if the special nature of the metric induced by the closed G2 structure gives you any restriction on the topology of M. So remember I said that closed G2 structures kind of depend on far fewer number of functions of variables than metrics. So this says that the metric induced by a closed G2 structure is quite special. So it might be interesting to see if the special properties imply any restriction on the topology of M. Now we know this doesn't happen for co-closed G2 structures. So it's not obvious that this would happen for closed G2 structures, but it might. In this direction, there are kind of 2 interesting results by others that I thought kind of are interesting. So there's this result by Robert, this kind of pinching inequality for the Ricci curvature of the metric induced by a closed G2 structure, which essentially says that on a compact manifold M, the traces Ricci curvature has to be, bigger than the scalar curvature in some sense. This kind of total traces Ricci curvature has to be bigger than the total scalar curvature in some sense. So the metric can't be too close to being Einstein. And the other, I think, interesting result is this result of Clayton and Ivanov that expresses this topological invariant. So if I take the first quadriagonal class of M that lives in degree 4, cup it with the cohomology class of the 3 form that lives in degree 3, so we get something in degree 7, and pair it with the fundamental class of M, I can express this as an integral of the second order invariants, these curvature invariants on my G2 manifold. So what's interesting about this is that this says this integral is actually a kind of invariant, topological invariant of my closed G2 structure. So if I vary within the cohomology class, this thing is going to stay the same. What's also interesting is that if, say I'm on the 7 sphere, then this cohomology class is 0. So actually this integral has to be 0 for the metric induced by some hypothetical closed G2 structure on the 7 sphere. Okay, so I just thought these were interesting, but I haven't got too much more to say about this. Okay, so now I want to move to kind of the main thing I want to talk about here, and this is a special case maybe of those 2 questions I posed at the start. So let's impose some extra condition on my metric. So what can I say about a closed G2 structure phi if its induced metric is conformally flat? And we're going to see that I can actually say everything that I would possibly want to say about the closed G2 structure. I can completely classify the closed G2 structures for which the induced metric is conformally flat. Okay, so just thinking about what does this equation really mean? So conformal flatness is equivalent to the vanishing of the Weyl curvature of G phi. So really I should maybe be saying locally conformally flat, but I think this conformal flatness is a standard terminology for this. So it's equivalent to the vanishing of the Weyl curvature of G phi. And that's a system of 168 second order PDEs for my closed G2 structure phi. And we get the metric from phi in a very nonlinear way. So it's kind of reasonable to expect that these are going to be nonlinear PDE. So it seems like, a very overdetermined problem. Now, if I have an overdetermined problem that appears in geometry, it's kind of very natural to approach it using kind of the method of moving frames and the theory of exterior differential systems. So that's what I'm going to do. So to do that, I need to talk a little bit about moving frames. I'm going to say the minimum possible. So I just want to talk about the kind of structure equations for closed G2 structures. So let's let phi be a closed G2 structure now, just an arbitrary one for the time being. Let B be the G2 coframe bundle of phi, which is a principal G2 subbundle of the coframe bundle of my manifold. And let's let omega denote the tautological 1 form on B, restricted to B. So on B, the Levi-Civita connection is going to split into a piece theta, which takes values in the Lie algebra of G2. So the Levi-Civita connection should take values in the Lie algebra of SO7. And the Lie algebra of SO7 under the group G2 splits into 2 pieces. It splits into the Lie algebra of G2 and a piece valued in R7. But when it's closed, the piece that lives in R7, what I call T of omega here, you can actually write it as T of omega, where T is some section of an associated bundle modeled actually on the Lie algebra of G2 itself. So this T represents the torsion 2 form, and tau it contains essentially the same information as the torsion 2 form. So our Levi-Civita connection splits, which means that Cartan's first structure equation splits as well. So Cartan's first structure equation would say that d omega is equal to minus the Levi-Civita connection wedge omega. But we have the splitting, so we still have this other connection form theta, so this natural connection on B, and then we have this torsion piece in my first structure equation. And then Cartan's second structure equation, which you can get together with the kind of Bianchi identity, this d squared of omega equals 0, imply the following structure equations. So T is a section of some bundle, and it says that dt plus the natural action of this G2 valued connection form on T itself is equal to this W27 piece, this W64 piece that I talked about before, plus terms that are quadratic in T. And then the curvature of this G2 connection theta can be expressed in terms of W27, W64, W77, and more terms that are quadratic in T. So these quadratic terms, I don't want to say what their exact form is, just kind of want to write this schematically. But these formula make sense because T is the torsion, it's first order. And so when we differentiate T, we should get second order invariance. And again, the curvature of this connection is a second order thing, so we should get second order invariance as well. So these three equations, the d omega equation, the dt equation, and the d theta equation, kind of make up the first set of the structure equations. So now let's assume that our induced metric is conformally flat. Well, that's equivalent to the vanishing of the val curvature, which is the vanishing then of W27, W64, and W77. So if we look at our equations, all these vanish, and our structure equations now become this set of equations. So these equations have the interesting feature that the right-hand sides, we already know how to differentiate them because we know how to compute d omega, dt, and d theta from the equations themselves. So we know how to differentiate the right-hand sides. Now, I've just said that when I have a closed G2 structure inducing a conformally flat metric, then the G2 coframe bundle admits an omega, theta, and t that satisfy these structure equations. Well, it's not too hard to show that conversely, if I just have some 21 manifold that has a coframe, omega, theta, so omega takes values in R7 and theta takes values in G2. So the components of these things will be 21 one forms. So if I have a 21 manifold that has a coframe made up of the components of omega and theta, and a function t that maps from my 21 manifold to R14, which is the Lie algebra of G2, that satisfy these equations, then I can identify n with the G2 coframe bundle of some closed G2 structure phi such that G phi is conformally flat. So the problem is then reduced completely to kind of a prescribed coframing problem. So what I want to do now, in order to construct these manifolds that have conform G2 structures with conformally flat metric, I want to find n with omega, theta, and t so that these equations are satisfied. That's a kind of a prescribed coframing problem. And these problems are very classical and the subject of quite powerful existence and uniqueness theorems that go back to Élie Cartan, his theorems generalizing Lie's third theorem. Now the relation with Lie's third theorem, takes a Lie algebra and constructs a Lie group. That would be the case if this t was kind of a constant. So if dt was 0, then that would be Lie's third theorem that you'd want to apply, but t is not constant. So this is why you need to use Cartan's generalizations of these theorems. Okay, so now applying one of these theorems of Cartan, what you need to do, you need to check that the equation d squared equals 0 is formally satisfied, which you could check, and it is in this case. So d squared equals 0 is formally satisfied. It doesn't introduce any new equations. So applying Cartan's result gives me the following theorem, which says that for any element of the Lie algebra of G2, I can find a closed G2 structure phi satisfying this conformal flatness condition on some neighborhood, some open neighborhood of the origin in R7, whose G2 coframe bundle contains some coframe for which the value of the torsion function t at this coframe is t0. So this is an existence part of the theorem. It says that, if you give me an element of the Lie algebra of G2, I can find a closed G2 structure with the metric conformally flat so that its torsion function attains that value. And furthermore, there's any unique, so there's the existence part, then there's a uniqueness part of the theorem that says that any two twice continuously differentiable closed G2 structures that satisfies this property with this T0, they're actually isomorphic on a neighborhood of 0 in R7. So what this theorem says then is that kind of germs of closed G2 structures with conformally flat metric are kind of determined by this T0, but there's a subtlety here. As I move up and down in the fibers of my coframe bundle, this function T is G2 equivariant. So as I move up and down the fibers of this coframe bundle, my T is going to move through the orbit of the adjoint action of G2 on the Lie algebra of G2. So the thing that really determines the germ of the G2 structure is not T. It's more like this kind of map that maps into the orbit space for the action of the adjoint action of G2 on its Lie algebra. So from kind of the existence and uniqueness part of this theorem, you get this result that says that the set of isomorphism classes of germs of closed G2 structures satisfying this conformal flatness condition is just in bijection, kind of roughly speaking, with this orbit space for the quotient of the action of the adjoint action of G2 on its Lie algebra, which you can actually identify then with the quotient of the a maximal torus in the Lie algebra. It's R2 quotiented by the action of the Val group for G2, which is D6. So then if I want to classify the closed G2 structures with G for conformally flat, well, I have an existence uniqueness theorem, but it doesn't quite say all the things I'd want it to say, because I don't really know what, my M is 7-dimensional, and I don't really know what the image of this T looks like inside this orbit space. But the uniqueness part says that the uniqueness part of the theorem says that to classify these things, it just suffices to produce enough examples to fill out this entire orbit space. If I can find one closed G2 structure with G phi conformally flat for each element of this orbit space, then the uniqueness part of the theorem will kind of say that I found everything possible. So here's a picture of this orbit space. So the orbit space is a Val chamber for G2. This is root diagram for G2. The orbit space is just this gray area extending out to infinity, this Val chamber. Well, there's one obvious element I can find. If I take just the standard torsion-free G2 structure in R7, just the flat one, then its torsion is 0. So it fills in the origin here. So I found a closed G2 structure that's conformally flat, whose torsion function has image of the origin. And it's possible to find then another, an incomplete closed G2 structure on R7 less the origin that fills out this line, this blue line extending out to infinity. And then it's possible to find an incomplete closed G2 structure on lambda 2 plus of CP2, where the image of the torsion function kind of looks like this. So it starts at some point on this maroon line, and then it sort of travels. So this is what happens at the 0 section. And then it travels out and is asymptotic to this other line. And rescaling my metric rescales the torsion function. So using these three, using this black dot, this blue line, and this purple line, together with scaling, I can fill out the entire gray area. And then with the uniqueness part of the previous theorem, this gives me the classification theorem. So the theorem says that if I have a closed G2 structure with locally conformally flat induced metric, then up to some constant rescaling, it's locally equivalent to one of the three examples that I described. So it's either flat R7, this incomplete metric, which is not flat on R7 less the origin, or this incomplete closed G2 structure on lambda 2 plus CP2. So this is a kind of a very strong rigidity thing. So I say it's a kind of locally equivalent, but actually we know exactly what it is. You would be able to get global results completely easily from this. Actually, the local is stronger than the global here, because I'm making no assumption on the kind of behavior here. So the corollary would be that if I want to assume, so I said these last two examples were incomplete. So if I add completeness to my hypotheses, then I get that my G2 structure must be the flat G2, must be locally equivalent to the flat G2 structure on R7. So actually kind of globally, that says that my manifold should be a quotient of R7 by some discrete group of G2 automorphisms. So really, if you want to have a closed G2 structure for which the metric is conformally flat and complete, then you've just got the flat one, maybe on some torus. Yeah, so this kind of was a nice result, I think, and it's very much a special case of those general two problems that I stated at the start. You might be tempted to ask what happens for co-closed G2 structures. Well, I don't know exactly, but I do know that the flat metric on, the constant curvature metric on S7 is induced by a nearly parallel G2 structure. So it's conformally flat. So there is, there are at least some kind of non-trivial compact examples in that case, but I don't know if that's everything. Okay. Yeah, so thank you.
Great. Let's thank Gavin. Questions for Gavin? We have 5 minutes or so before the break, so a little more time for questions here.
So connecting with something Robert said, is there a general discussion about a Riemannian manifold which admits a calibration? A closed G2 structure would be calibrated in 3 dimensions, I suppose. So.
Yeah, well, I think that the problem even on R7 or on Rn of classifying calibrations is already quite hard. So you might need to make some kind of extra. Yeah, I think just saying I have a Riemannian manifold with calibration, I'm not sure. The calibration, might not even have calibrated submanifolds. So you might need to say something more, a bit more conditions.
Simon Salomon had a question.
Maybe he's muted. Is Simon there?
Okay. Simon should be unmuted now, it looks like.
Can you hear me now?
Yeah, yeah. Yeah.
No, never mind, forget it. I'll put it in the chat. I'll put this thing in the chat.
Okay. Yeah, maybe you're on a delay or something.
Can you hear me now?
Yes.
Yeah.
Sorry, can you hear me now?
Yes.
Yeah.
Sorry, I had a microphone problem. I just wanted to ask quickly. So, I mean, the examples you gave, is there anything special about the sort of the points in the vial chamber for which the stabilizer is a U2?
Yeah. So, sorry, I'll share again. Yeah. Yeah. So these points on this purple vial chamber. So for this purple G2 structure here, this is the 0 section in this lambda 2 plus of CP2, and this is the point where the torsion has a U2 plus stabilizer, as I called it.
Right.
And then for this other G2 structure, for this blue,
Okay, I see.
this has the U2 minus. Yeah.
Okay. Okay.
Exactly.
Thanks. Thank you.
Are there any other questions for Gavin?
Oh, I have one. You said the R7 minus 0 is incomplete. Is it incomplete in both directions?
It has a singularity at 0, say, and I think it's incomplete in the other direction as well. Yeah. It's actually possible for all the examples. They're all cohomogeneity 1, and you can write out the kind of function that makes them conformal to the flat metric or to the metric on S7. You can write that out explicitly, so you can kind of see exactly to what degree they're incomplete somehow by that.
Right.
And that function is always invariant under the action of the acting group as well. You can do that.
Right.
Yeah, it was interesting to me that lambda 2 plus of CP2, you can actually view it as a kind of there's a map then into S7, which is kind of interesting. By kind of excising some set, you then get something that's diffeomorphic to lambda 2 plus of CP2.
Huh.
It comes from the action of SU3 on its Lie algebra.
Okay.
Does anyone else have any questions for Gavin? Okay, if not, then let's thank Kevin again.